placer para mí to introduce you to Michael Rieth. He comes from the Karlsruhe Institute of Technology. As you can see here, he's in the Institute of Applied Materials. He's going to talk us about materials, technology, and applications in nuclear fusion. Well, Michael is a Master of Science in Electrical Engineering by the University of Karlsruhe, and also Doctor in Physics by the University of Patras. This was a great surprise for me because I have a student from Patras also. Well, she is very interested in know about you and your experience in Greece. From 1995 to 1999, he was researcher in the Institute of Materials Research in the Sfcm, and from 1999 to 2000, he was a researcher in the Engineering Science Department of the University of Patras. Later, he was in the Applied Materials Institute at the KIT, and from 2008 to 2012, he has been co-chairing the EFTA topical group on fusion materials, and from 2011 he is the head of high temperature materials group in the Institute of Advanced Materials, and also from last year he is the project leader of materials in Eurofusion. He has been working in materials and technology development and for the power applications, focused mainly in fusion energy, and also in atomistic modeling of metallic materials and nanosystems. Well, it is really a pleasure to enjoy his presence here, and well, I think that you are going to enjoy it as much as me, so that the time is yours, Michael, and when you want, you can start.
Thank you very much, Jose, and thank you very much for inviting me. It's a big honor for me and also a great pleasure of being here. And well, the first part of the seminar, I would like to focus on a material which is less common in engineering sciences, and that's tungsten. So, a brief outline of the seminar. I will show you a typical application, the production of tungsten, the difficulties or not so much difficulties of machining tungsten. Then the main problem with tungsten is brittleness, the influence of the texture of the material on the brittleness, and then I will show you some specific developments which result from all this specific materials behavior, with a focus on fusion applications. The main problem is to try to make tungsten ductile. That's a part of the final session. Let's quickly start with applications. The biggest reserves of tungsten is in China, with about 60% of the world resources, followed by Canada, Russia, United States, and well, the rest is more or less distributed among South America and Europe. Typical applications are fabrication of cemented carbides. That's probably 2/3 of all applications of tungsten. Another third deals with alloying steels. This is mainly done in China and Russia. They spend more than 20% of tungsten to alloy steels. And interestingly enough, in Europe, we more or less avoid tungsten or use tungsten only to a minor part for alloying, because here we substitute it by molybdenum. Another area is simply to fabricate mill products, plates, rods, wires, things like that, and the rest are others. Here are a few examples. Cemented carbides. They are mainly used for the fabrication and production of tools, small bits or large bits, mainly for drilling big holes in euros or metals, for turning or grinding, milling. For steel production, as I said, there are very specific high-speed steels which amount or use several weight percent of tungsten as alloying element, for example, for turbine blades, very specific steels. Then there are heavy metals, so-called heavy metals. These are two-phase materials of tungsten, and its main use is to make use of the weight. So, for example, in a Boeing jet, you all know, there are counterweights to balance the flaps and slats, and that's typically around 800 kilograms of such counterweights used here in these parts of the blades. Very funny or not so funny application is its use for so-called green ammunition to die in a healthy way, but well, forget it. Then of course military applications for armor piercing ammunition, and a smaller part goes into the lamp industry where wires of several shapes and kinds are used to produce lamps. And as weld electrodes, for example, that's another common use for tungsten materials. Also in electric industry for high power switches, but also for any kind of high temperature application, furnaces and things like that, also in glass industry. And of course, a minor part goes also into X-ray tubes for the rotating anodes or cathodes. And finally, a tiny amount of tungsten is used in electronics. In fusion application, however, the thing is quite different. This is one of the oldest design for a so-called divertor. That's the thermally highest load part in a fusion reactor. And here you see two typical applications. This is a single finger, a cooling finger with helium cooling. Helium is pressurized through holes, and then by jet cooling it removes heat from this part in red. This is sort of being made of tungsten material. It's a structural application because it's pressurized by about 10 MPa. And on top of it we have a tungsten block of some kind, and this, its only use is to shield or to protect the cooling structure from the plasma interaction. We have a very high heat load, about 10 megawatts per square meter. That's an immense heat load. And if you assemble a few 100,000 of such fingers together, you can fill in an area, a cooling area on such diverter cassettes, which are arranged circular inside the reactor. And yeah, so there are two typical applications. This one for armor, for protection, and another one as a structural material. There are some other design ideas which make use of tungsten, or which try to fabricate such diverter blades completely out of tungsten with cooling channels, all made of tungsten blades. They have to be braced together in some way. They also use these jet cooling cartridges, and they also use tungsten as an armor part on top in many different ways. Another idea is to use, again, tungsten as a cooling structure in the form of a pipe. Then to increase the cooling area, the metallic foam is inserted here, and helium is pressed through this foam also to remove heat. And more in detail, it looks like that. That's the magnified view of the foam. And so together we have cooling structure, again with an increased surface for increased cooling rates, and tungsten armor on top, but bottom and side walls, everything is made of tungsten plates, or at least that's the idea of this design. Let's quickly summarize diffusion application. We have one application to protect substructures where tungsten more or less is eroded away by the interaction with plasma and incidental particles. It's used in divertors, but also to shield the whole surface inside the fusion reactor. And here we have high heat fluxes and also high thermal gradients. Then there is a structural application for helium-cooled divertors where the operating temperature is lower. Cyclic loading has to be taken into account. We have pressurized cooling channels. Many things have to be joined, and the interaction with the coolant might be important. But also neutron irradiation damage. We will come to that later. Now let's quickly go through the production of tungsten. In industry it started by tungsten ore or tungsten oxide powder, then that's reduced under hydrogen atmosphere at rather high temperatures, and then the result is pure tungsten powder. This is pressed, then it looks like that. After that it's sintered, it shrinks a little bit, then it looks like that. Thereafter it is thermomechanically treated, which means at various but rather high temperatures rolled or forged or whatever deformed. The reason is pure powder has a very low density, around 15 or so%. If you press it, if you cold press it isostatically, you can reach densities around 60% max. After sintering, density increased significantly, but still the maximum you can reach during sintering ends at around 98% or so, so there is still porosity, which you don't want to have usually in the material. And to reach the 100% density, you have to deform the material significantly. So this is the usual commercial fabrication or production. Besides pure tungsten and tungsten carbides, there are roughly 3 groups of tungsten materials. One is the most often referred to ODS tungsten, or I prefer grain stabilized tungsten, which means to the tungsten powder we add some carbides or oxides as a second phase in the low % range. Or for the case of lighting industry, for bulk wires, very strange thing, but that's true, potassium is added. And, well, this is most often used or only used for wire fabrication, and which produces the so-called non-sag wires in, well, not in this one, but you know, the old bulbs, which with the wires inside. The oxide and carbides are mainly used for weld electrode materials, and very prominent are lanthanum oxide, that's lantana, or cerium oxide, thorium oxide. All this is made for weld electrodes. Then the heavy metals, tungsten heavy metals, you remember, for counterbalancing or weight applications. They are mainly used just for functional applications due to their weight and easy production method. They are sintered in a liquid phase, which means the second phase, which is either nickel iron alloy or simply copper, is melted with the tungsten particle inside, and this results in a dense and weightful material. Solid solution alloys are not frequently used. There is only one commercially alloy, that's tungsten rhenium, with a maximum content of 26% of rhenium. Many other alloys are thinkable. I will come to these back in a minute. But compared to other alloying, this is not done melt metallurgically. All these alloys, or especially tungsten rhenium, they are fabricated also by sintering. That's a mix of melting and sintering, so sometimes that's called smelting. And the classical precipitation hardening mechanism doesn't work here because it's not melting. Quick summary: commercial production routes based mainly on industrial sintering and hot forming. That's where we get semi-finished or mill products. Potential tungsten materials for fusion applications could be pure tungsten, potassium doped tungsten, tungsten solid solutions, grain stabilized tungstens, or if we think of these heavy metals, only tungsten cover might be an option here. What about machining of tungsten? Here we have pure tungsten on the right hand side. This two-phase or grain stabilized tungsten is lantana, and if you see some turning experiments, it more or less behaves like any other metal you can turn, and maybe it's not so easily recognizable on these movies, but the pure tungsten is harder to machine, and this grain stabilized tungsten, they produce finer chips. The chipping behavior is more favorable. They are better to machine. The surface quality by this conventional machining is quite good, perfect, not to say. So milling, grinding, turning is not a problem. Electro-discharge machining is also no problem, can be easily done. But as you can see here, this induces many and quite deep surface fractures. So another type of machining, electrochemical machining, has been invented. I don't want to go into details here. It's a typical electrochemical fabrication process. Here we can shape and vary surface of tungsten by different tools. Here are just a few examples. But the main advantage here is that it doesn't induce these cracks as in the electro-discharge machine. You see it here. This is after EDM, after discharge machining, and here the surface by electrochemical machining, which is without cracks or almost without cracks. Also here, quick summary. Classical machining is possible, turning, milling, grinding, etc. That's let's say a big problem. The ODS tungsten is easiest to machine. Electro-discharge machining is possible, but surface cracks are induced and we don't like to have them. Electrochemical machining is also possible. It's preferable to electro-discharge machining because you can polish the surface, finish the surface, and also use it for crack removal or surface structuring. Now let's come to the main drawback of tungsten, that's its brittleness. And you see here choppy impact during the very first phase of the test, and as soon as the hammer contacts the specimen, here is a variety of tungsten material, you see an immediate fast fracture which goes completely through the material or through the specimen. Here a sequence, this is the start, and right after about 20 microseconds you see already fast fracture evolve, and well, after 50 microseconds or so the cracks have already gone through the 3 mm of the specimen type. So this is a real brittle material. These tests have been performed at room temperature. Now the question is, where do we see the ductile transition temperature? we make a jump now up to 1100 C, and on the left hand side you see sintered tungsten, and even at 1100 centigrades the material doesn't change its behavior. It still shows fast fracture. But the tungsten rod on the right hand side, you see, behaves as we know it from steel. At moderate temperature, it's a ductile fracture without fast crack involvement. Again, sharp impact test of tungsten rod in the middle and sintered tungsten on the top. And on the bottom, this is compared to steel, all at room temperature. We would like to have the fracture behavior from, as we can see or observe it in steel at the bottom. And now to really visualize the brittleness and problem with tungsten, there is just another, let's say, funny test which we have invented, or well, you know, scientists also like to play around a little bit. That's the so-called air gun test. We used an air gun and shot it on a Sharpie specimen sample out of sintered tungsten, and here on a very or rather big or thick plate of tungsten 5% tantalum, and look what happens. Well, in the first case, the sintered tungsten, you see not only one crack or one fracture, it virtually scatters into pieces, and also the thick plate on the top, it's fracturing in a very impressive way. Impressive means, well, I cannot think of any structural application with such a material if you see such a test and behavior. This is what we would like to have again, the same test with a 9% chromium steel, and you see the steel is not much impressed by this air gun bullet. It just bends a little bit, and that's it. No fracture at all. And this is what we typically would like in engineering material for structural application with such a behavior. Now let's come to the fracture in the sintered tungsten. Sintered tungsten, as mentioned, has not a very high density. It's varies somewhere between 90 and 100%. Nevertheless, it shows almost always intergranular fracture, and as you have seen, there is a rather high DVDT, if at all. We haven't performed tests higher than 1100 C, but up to 1100 C there was no ductile fracture. So most often we see this intergranular fracture, and if you look at this grain, only sometimes we observe transgranular fracture. That's a general fracture behavior of tungsten. And let's summarize with respect to brittleness. We have a very high brittle to ductile transition temperature in tungsten, especially in sintered tungsten. DVDT is higher than 1000 C. There is an easy intergranular fast fracture, which means we have weak grain boundaries. That's very specific to tungsten. The grains are not bound together, they are weak. That's the main drawback, and this is rather specific to tungsten. Only molybdenum is more or less comparable to that behavior. Now let's compare this to rolled or formed tungsten, which show a specific texture. On the left-hand side, we see as sintered tungsten, the typical polycrystalline microstructure, grains, homogeneously distributed. On the right-hand side, the same material as rolled. And in general, hot forming in tungsten is performed by rolling, so for plate fabrication, or forging. That's less common, but you can still produce semi-finished products like small round blanks. And of course, rods are also fabricated mainly or most often by rolling or swaging. This is the rod structure, elongated grains along the rolling or forging direction. You see all this specific microstructure here in rolling direction. And with a higher magnification, if we have, for example, lanthanum oxide mixed to the powder, then lanthanum forms small second phase needles along the grain boundaries. And inside the pure tungsten rods, you also see the elongated grains or sometimes sub-grains here. The plate microstructure is comparable, but since it's rolled, there is a slight difference. There are no needles. It's more like flat or flattened grains, and yeah, this is a graph which explains it probably better. It's like a pancake structure which we result in after rolling. Now we have made the impact tests of such textured tungsten materials, pure tungsten. And here we have Sharpie energy over the testing temperature, and what you see immediately, only the rod material shows a very high or sufficient high toughness, that's Sharpie energy, whereas all the plates or round blanks are, well, lower by at least half. Then another thing comes immediately into view. We have not only one transition for the case of the rods, but a second transition. There is the one, there is the two. And this is typically for tungsten. Fractures in two different types. One is the classical brittle fracture. Then we have delamination fracture, that's indeed ranged here between. And only tungsten rods show fully ductile fracture at higher temperatures, at least in this configuration. Why is that? Let's compare the microstructure. Rods, as seen, can be considered as a bundle of fibers. It's like a fibrous material, whereas plates are more or less a stack of pancakes, if you want. And now what we have said is tungsten has very weak grain boundaries, so if you load a bundle of fibers, in this case, with this tensile stress, then the grain boundaries experience full load. And since the grain boundaries are weak, they easily fracture. So we have intergranular fracture, and depending on the oxides, which might be also mixed to the material, this behavior might even be enhanced. In some other cases, the opposite. And of course, the same is true for plates or round planks. If you load the pancakes in this way, you have easy fracture. That's not so good. On the other hand, if we load the material along the rolling direction, that's along the fibers or along the platelets or pancakes, then the material doesn't fracture so easily, because here the grain boundaries are much less, and as a conclusion, you have to avoid in a technical application or structural application this type of loading, and this is the best orientation which you can load the material. Now here, this is what I have called delamination fracture. You see the fracture does not go through the specimen, it develops along the grain boundaries, along the rolling direction, along the elongated grains or platelets. This is very typical to tungsten materials. But in a fusion application, we don't need rods or plates or whatsoever. We want to have pipes or cooling structure. So what can you do with a rod? We have seen rod behavior is best compared to all other semi-finished products. And well, a very simple idea is to use a rod, drill a hole in it, and then you result in a pipe. It's like here. You can do this with steel. We have put this small pipe of steel in the sharpie testing device, and the hammer deformed this piece of pipe, and well, you don't see any fracture. This is what a structural material should behave like. If you do the same with a tungsten rod, you unfortunately end up with with several pieces of shards. That doesn't work with tungsten rod material, and this is simply due to the microstructure and due to the unfavorable orientation of the grains here. So that's useless. Delamination fracturing plates look similar. You see it here. Also crack evolution not perpendicular through the specimen, but along the rolling direction. And now we have done sharpie tests to see this more clearly. In this orientation, we expect then the best possible behavior, and this orientation, this should show easy crack evolution through the pancakes. And indeed, if you do the tests, the best results are this curve with very high energies. And in this orientation, you can see, well, sharpie energy measured is around 0. That's nothing. So that's easy fracture, and that's why we have to avoid this type of loading. If we would rotate this specimen by 90 degrees, then the pancakes would be loaded in the second best orientation. And you see, if you load them through, then you see in the crack such laminar structure, which are due to plastic deformation, and this corresponds to this line. So indeed, in 2 dimensions, in the surfaces, we can load plates easily. That's not a problem, but we have to avoid this type of loading, this orientation. Finally, impurities are also relevant to these materials, but not so much. This gives just a brief or a first idea of this. We have here in red industrially pure tungsten and ultra high pure tungsten. You see there is a small shift in DPDT, but not so much. So in general, we can say industrially pure tungsten would be sufficient for any applications. So hot worked tungsten shows a brittle delamination transition. Only pure tungsten shows delamination ductile transition in the case of rods, and impurities increase transition temperatures a bit. And the microstructure anisotropy of hot worked texture is that we see easy delamination fracture along the textures. Oxides or carbides like lantana can slightly lower transition temperature, but also, depending on the case, increase that. And the question is currently, and that's already an important topic in material sciences, are there second phases which can strengthen the grain boundaries? If we would find this, this would improve the material properties significantly. Or in general, are there more ductile tungsten alloys available? That's the big question, and if anybody of you has an immediate answer, I would be very happy to hear. Use of semi-finished milled products. We have seen that rods are more or less useless, and plates might be used to fabricate cooling structures. And well, if you work with plates, then an immediate idea, namely deep drawing or bending, comes into play. And this is part of some very specific developments in fusion technology. We have done this. We have tried to fabricate these fingers for the divertor application I have shown at the beginning by deep drawing, and indeed, you see, it is more or less feasible. However, it needs well, only medium temperatures. Let's say 600 to 800 C is perfectly enough to deep draw these materials, also to bend these plates. But the bending rate or deep drawing rate is so slow, with about 1 millimeter in this case per minute, that the usual benefit of this method, namely mass fabrication, fabricate such parts by the thousands or millions, is not possible anymore. Then, especially to produce armour parts of tungsten, we have developed a powder metallurgical process based on powder injection molding, which you might know. There is powder mixed with a binding phase, then this is kneaded to a mass. This mass, or this so-called feedstock, is then pressed into tools in a powder injection molding machine, and finally by sintering to remove the binder and or dipping or further sintering, you can end up with very good finished parts. Here is how it goes or looks like. This is a machine with a filled tungsten powder binder feedstock. Here you see one half of the tool. This produces hexagonally shaped armour parts. That's the other part of the machine. Then the tool is pressed together. Then the feedstock injected into the tool. This happens at around 200 centigrades or so. That's enough, but with a high pressure. And so finally you end up with the green part. That's the pressed tungsten part. And after this, the part is sintered, as said. Then it shrinks, always during sintering, and you end up with nearly, or very good, or rather good, near net shape parts. This machining tool we have now misused, let's say misused also, as a rapid development tool for material, because it's rather easy to mix up several tungsten compositions, fabricate a plate or whatever by this machine, and so you can screen rather quickly the effect of alloying. This has been done for pure tungsten as a reference, with yttria, with lantana, with titanium carbide, tantalum carbide in various percentages. And you see the second phases here. That's the more or less small dots inside the tungsten matrix. And to have a rather quick overview on the behavior, we use 4-point bending tests with a low strain rate, so temperatures up to 500 C are already sufficient to see what happens. And in pure tungsten, you see it down there. At a very low temperature, we have rather brittle fracture without any plastic deformation. At 300 C, the specimen will start to be bended, and well, at 400 C, there is a sharp transition. 380, 400 C, the specimen doesn't break anymore. So this is the behavior we would like to have for structural materials, and with such screening and testing, you can quickly develop other or different materials. So that's brittle fracture, ductile fracture. This is what we want to have, and want to have it to appear at very low temperature, as low as possible. Next step in the development of this material is to test them for their armour applicability. This means we have to load them with immense or with high heat load, and the worst case scenario is not only high heat load, but shock loading. That's short pulses by electron beam with a very high heat load. And after 1000 shots, materials look like that. The pure tungsten shows almost no change. But for example, here you see a crack network, and also the other one shows a crack network, and this is what you don't want to have. So with this type of test, we qualify the material for their armour behavior. Again, we did this test, the same test. This is 1,000 shots. This is a commercially fabricated plate. We see cracks on the surface of the testing, and with this pure powder injection molded tungsten, you don't see. So there seem to be some benefits for this material. Thermal shock load or a thermal high heat flux test, that's not shock loading. This has been done in a facility in Garden, you see it here. It's inside the vacuum chamber, and this is loaded by immense hydrogen, and sometimes a mix of hydrogen and helium particles. And well, you see it on the color, it's very bright, so the surface temperatures, I think in that case, are around 1500 C or so. It's tested also with pulses or not, you can do it as you want. And after the test, you can see how the material behaves. What I want only mention very quickly, because you see it very clearly here, oxidation in air is very problematic for tungsten. At 500 C, nothing happens, only the surface blankens a bit, but then it stays for years in this way. But at 600 C, you see what happens to the blade. It behaves somewhat like croissant. If you put it in the furnace, they really bake up, they split into multi-layers, and they really lose their form at higher temperatures. If you see here, this has nothing to do with the blade anymore. So oxidation is a killing factor for tungsten application, as you can see. And we have done the same for this powder injection molded part, and even at 700 C and even after 4 days in the furnace in usual air, well, it oxidates, that's clear, but you can still recognize at least the original shape. So it seems that also here, powder injection molded tungsten parts show at least some advantages. Preferred production rules now are industrial sintering and hot forming. That's the only way from industry, but also powder injection molding would be a viable way to mass fabricate at least armour materials or armour parts out of tungsten. Bending and deep drawing is possible. The drawback here is that it goes very slowly, so it certainly is not a mass fabrication method. And well, we can also use, as you have seen, powder injection molding as a tool for rapid prototyping of tungsten alloys. Now let's come to the final chapter, ductilization by solid solution. This was once an idea when we started all these applications or studies on tungsten. We still believe or thought that it would be possible to ductilize pure tungsten by addition of solid solutes. Now if we have a look on the elementary table, insoluble are in white. The intermetallic phase formers with tungstens are in red. These are very specific intermetallic phases, line compounds, they are in dark red. And what remains for solid solution is only titanium, vanadium, niobium, molybdenum, and tantalum. And to a small amount, as we have also mentioned, rhenium, and well, even less, osmium, ruthenium, and rhodium. We have produced this material, or at least Clancy, the manufacturer, has produced this material, and you see immediately the difference from the microstructure. This is pure tungsten, and here is the measure, 50 micrometer, whereas here we have to measure with 20 micrometers. You see one effect immediately. The addition of solid solutions or solutes produce a much more finer grain. So in the end, what would we expect with a finer grain? That's a classical hardening mechanism, makes the material more hard or harder. And if you compare all these several materials with this blue line and dotted line as a reference, that's ultra high purity tungsten specimens. And all these are the solid solution materials. You see they are much more brittle, so in principle nothing was won by this investigation. And as a summary, if you add tungsten with a variety of materials, it makes tungsten even more brittle as it already is. So that's not a good solution. The only effect we know, positive effect, is on tungsten to ductilize rhenium and to a small amount iridium, but these elements are so expensive that you cannot afford the material for fusion applications. So hardening by solution and fine grain increases the brittleness of tungsten, and for a large scale application as we would need it in fusion, we have to live with the intrinsic brittleness of tungsten. This is the main conclusion and result. And this leads finally to another way to produce ductile tungsten materials. And if you see this test, this is a stack of tungsten foils at room temperature, and you can bend it very easily without any fracturing. It even behaves ductile. So, well, why do we not use tungsten foils? Of course, you cannot build up a whole power plant by tungsten foils. That's not possible. And at the same time, this is the question, can we make use out of this behavior of tungsten foils? First, let us quickly look on a tungsten foil. It has a very specific texture due to the severe rolling of the foils. The grains are oriented in a 011 direction, in a 100 planes. And if you heat treat this foil up to 900 C, after heating it up to 900 C and cooling it down, nothing happens inside the material. It still can be bent, it shows plasticity, but starting from 1000 to about 1200 centigrades, you see cracks which are typically in 45 degrees to the rolling direction, and this is due that we have this texture in this direction and the cracking planes are usually in this direction, so something happens in the foil which makes them more brittle. And if you go higher with temperature, then recrystallization starts and another change of cracking starts inside the foil. So as a conclusion, operating temperature and working temperature of this tungsten foil is restricted to around 900 C. But well, still, compared to steel, that's something. The main question, what are the advantages of foil compared to bulk tungsten? And we investigated to layer foils within the layers to preserve this ductile behavior, and tried to receive some benefit out of this. And in the case of Chauby specimens, first have a look on this curve. That's the best available plates we have tested. This is a 4mm plate, and DVDT was around between 400 and 500 C. And if we compare this with such a laminated stack of tungsten foils with an inner layer of copper, you see DVDT is improved by 300 C. That's an immense improvement. And after fully recrystallization, if we recrystallize this tungsten plate, this massive plate of 4mm, if you recrystallize it and then test it again, you will observe even at 1000 centigrades in the Chauby test machine, no energy at all. So it's completely brittle. But the laminated material still shows some ductility at 500 C, so in that case we would even have an improvement by 500 C. And this is proof that in principle this is the right way. We have tested several inner layers, copper, titanium, zirconium, with more or less good results. You can see it here. And in principle, the question was, can we make pipes out of such structures? Because this is the ultimate goal. We need cooling applications, how to do pipes. And the typical fabrication route looks, in the first step, oxide removal from the surface of the tungsten, then in the layer deposition, then we join the whole thing together and perform some aging tests to see whether we can use the structures for a few years. And pipes can be simply produced, as we have seen, by rolling. We wrap up these foils and then join them together, and in the end we result in pipes. The advantage over a rod with a hole drilled inside, where we have this unfavorable grain distribution. Here the platelets or pancakes in the foil is oriented circumferential around the pipe, which makes the best possible load and application for such a structure. With that, some idea arose that we can produce maybe larger pipes, stick some armour parts on it. To test that in general, we have performed such tests with 100 megapascal pressurized test. Foil survived, no problem. Then these are also some studies and ideas, small mock-ups, where you can see a pipe inside. This is a tungsten laminate pipe, then a tungsten monoblock as armour parts surrounded. And inside we use also a pipe with holes in it to facilitate this jet cooling, as we have seen it in the finger design. This all works, but for technical readiness, we have not only produced these pipes, we have not only tested it, we not only made burst tests with the samples. We had also done some high heat flux tests here in Spain at the Plataforma Solar de Almeria also. And this is not exactly fusion on Earth, it's fusion in the sun, but still high heat flux application, and it was quite impressive. This is again a high heat flux test in Garmin, which shows a worst case scenario where we have used stainless steel pipe with has not the very best thermal conductivity and bends very strongly under such heat loads, but still the tungsten cover layer in between fixed the differences of thermal expansion, as we have seen. So in general, we have done all the technology. Of course, it's still a long way to go to fusion reactors, but the conclusions and outlooks are that we can have a material at least up to 900 C. There are still design constrictions for such laminates. Out-of-plane stresses have to be avoided, of course, and possible service temperatures of tungsten laminates depend strongly on the inner layer. We are hopefully we will find some better inner layers to operate such pipes at higher temperatures, and that's also part of the ongoing investigations. However, there is only one topic which could or maybe will be the ultimate showstopper, we don't know yet, and that's neutron irradiation and the embrittlement. This will be also part of the lessons today, what happens in materials during and after neutron irradiation. And I think and I hope that this was a relatively informative overview on tungsten and its use in fusion applications.
Most of the issues we have to solve concerning the exposure of tungsten to the flexible or high power materials in divertor are related to the surface itself rather than the bulk. I mean, there are many issues concerning the properties of the surface as compared to the bulk, like for example surface melting, fuzzy development by helium or hydrogen sputtering, and so on. So all these solutions we are foreseeing, like lamination with other components, how they behave in terms of these surface issues? Do you have an indication of that?
Yes. First of all, these laminate materials are not used for surface applications. They are just the structural cooling, let's say pipes, and they have to be surrounded by massive blocks of tungsten. And these massive blocks, which is the second application, armour materials, they have to deal and solve the problem with surface effects with regard to plasma surface interactions. And you are completely right. For these armour applications, we have to avoid surface melting, because this is the death of any structure. And also there is some complicated in the relationship, which is not completely known yet, which depends on the incidenting particles, helium, tritium, hydrogen, and plasma interaction, and heat load, and cyclic loading, and things like that, plus neutron irradiation. But as far as we know of today, we can live with a sacrificial layer of a few millimeters during the whole lifetime of such a component. And world's or best estimations have shown that all these other effects you mentioned may speed up the erosion rate, but not by an order of magnitude, probably only by a factor of 2 or less. And so in the end, we have to live with that.
So what is the status of the tungsten solution facing a demo reactor? Not ITER, but demo reactor.
There is no final solution yet. As you have seen, we have a variety of these powder injection molded tungsten grades, and this is also one of the most interesting research topics, to test them under many of these high heat load and plasma wall interaction conditions, and see which material behaves best, and to understand the mechanism.
Thank you.
Thank you. Continuing in the same line of the surface, and do you think that this surface, regarding, for example, neutron embrittlement and other purposes caused by high radiation, could benefit from selective treatments inducing modified microstructure, as for example inducing density of these locations by produced, for example, by laser or by shot pinning?
Are you referring to the armour application or to the structural application?
To the structural applications, mostly. Or maybe whatever implying a surface that can be modified in order to avoid, for example, embrittlement, or even to provide higher toughness.
As far as we know as of today, tungsten always embrittles severely under neutron irradiation up to around 900 C or even 1000 centigrades. Above 1000 centigrades, we don't expect embrittlement, because then the temperatures are high enough to self-anneal or whatsoever. So for armour applications where we have to, or where we deal with temperatures up to 1800 C or so, I have no worries. The problem is indeed in the structural application. And here the same is true, which is true for all materials. Microstructure plays an important role in the development of irradiation hardening. But to prove this and investigate this, we first had to do experiments on these materials, and unfortunately up to now there was no investigation. So we are operating on best guesses up to now.
Okay.
Any other question? No? Well, thank you very much, Michael. And we have now time for rest for a coffee, and we will return at 11:30 to the course. Thank you very much.